In this video, we're going to continue our discussion of closure to help us do integrals of real variables inside of real valued functions. This is our overview slide, which we'll spend about 5 minutes on before we go over each of our new topics in more detail and with more examples. First, just to review closure, we said if W max, and W max is the maximum value that a real function w of x will take on an interval. If it shrinks to 0 faster than 1 over r, then a real valued integral from negative infinity to infinity of wx is equal to the integral over a closed curve of wz, which by the residue theorem is equal to 2 pi I times the sum of the residues of wz inside C. The picture to go along with this idea is we're on the real line here and we're integrating some function, a real function of a real variable wx along the real axis. And because we're integrating only along the real axis, we're only plugging in real values of x here. But what we do is we extend our function to the complex plane, and in particular we say we're still going to restrict our integral on the real line, except that we add this extra curve, this semicircular curve on top, so that of infinite radius, so that we have this closed curve now and can use the Cauchy residue theorem. One thing that our previous video had depended on is the integral on this semicircle is equal to 0. So when we integrate over the closed curve, we don't add anything to the integral over the real line. In this video, we are going to look at one strategy for possibly dealing with closure with non-zero contributions, that is, the integral over the arc is not equal to 0. So the integral along the added segment, that's the semicircle here, used to create a closed contour does not equal 0, we must subtract off the added contribution. So in other words, our real valued integral from negative infinity is equal to our complex integral integrated over the real line, which is equal to our closed contour minus the added contribution. In our example, we will be using this formula as well as a new additional contour. So instead of the semicircle, we're going to have a rectangle. The next topic we will cover will be the principal part of an integral, which helps us deal with the case when the real integral has a singularity for some value of x over the range of integration. In general, the value of the integral is undefined, but we evaluate many of these real integrals of this nature using the principal part, which takes the original integral and removes the infinitesimal region around the singularity. And this is the picture that goes along with the idea. We want to integrate along this real axis, but we have a singularity at the point A. We do our regular addition of the semicircle on top so we can have a closed contour, but then we also do this path deformation so when we go around the singularity of A, what we end up with is we define something called the principal part, that's PP, of our integral from negative infinity to infinity of our real valued function w on a real variable x. So again, we're integrating along this real axis, except that we have the singularity A. And the principal part of this integral is defined to be the limit as epsilon approaches 0. Epsilon is our little radius around A, of the integral from negative infinity to A minus epsilon, this little portion here of wx, plus A plus infinity over here to infinity, that's A plus epsilon, that's this little thing here, to epsilon of w of x. So in effect, we've just taken this little portion of the integral out and we take epsilon to approach 0. Now our closed curve integral is equal to the principal part, that's this straight line with this little circle that removes a, but we need to add back, because we've taken it out in the principal part, we need to add back this little circle. So we have this U shape. It's to suggest this this right side circle, this open circle pointing up along WZ. And then for the closed curve, we're still going to add that semicircle on top, which will denote with the upside down U to denote this shape of the circle of WZ. We will definitely do an example problem with this. Our final topic will be definite integrals with sines and cosines, and for this topic we're going to use this formula for sine and this formula for cosine that we had discussed in one of our very early videos about complex analysis. It was something like elementary functions or something. So we extended the sine function to the complex plane, and we have this formula here that sine of theta is equal to 1 over 2I times e to the I theta minus e to the minus I theta. And we can write that as 1 over 2I, then z minus 1 over z. We have a similar formula for cosine where we have 1/2 e to the I theta plus e to the I theta equals 1/2 z plus 1/2 z. We'll plug that in to develop a formula here when we integrate a function of sine and cosine, and this is our formula that we use on our closed integral. And again, we have an example to illustrate this. That wraps up our overview, so we're going to start now up here with closure with non-zero contributions. The idea is simple enough. If the integral along the added segment, that's the semicircle here, used to create a closed contour does not equal 0, we must subtract off the added contribution. So here we have our original real valued integral over negative infinity to infinity, which we say is equal to the complex valued function, or we extend it to the complex valued function, but we integrate only over the real line. And that will be our closed contour integral minus the semicircle integral. We'll do an example, but which we evaluate I, which is equal to the integral from negative infinity to infinity of e to the x over 2 divided by 1 plus cosh x. And the first thing we do with our integral is convert it or extend it to the complex plane. We're integrating over the real axis e to the z over 2 over 1 plus cosh z. For this problem, it turns out that if we created the closed contour by using this semicircle in the upper half of the complex plane, we have two problems. The first is the complex integral does not vanish as r approaches infinity. In other words, we haven't met our condition over here at the top of the thing, top of our page, that says that W max shrinks to 0 faster than 1 over r. So our integral over the semicircle is not going to equal to 0. And the problem is that we have our function will be oscillating. It doesn't actually go to 0. And one thing to note, now that we're no longer in this chapter, your text actually doesn't use this condition so much as just showing the function will vanish to 0. The second problem is there are an infinite number of poles. In other words, this function becomes infinite or diverges anytime z is equal to plus or minus 2n plus 1 I pi, which means all the poles are along the imaginary axis and will give us problems. To solve this, we're going to use a contour, this contour here, which encloses only a single point at z equals I pi, the first positive one. So our contour is going to go from a negative x naught to x naught. It goes up 2 pi units, and then we're over here at 2 pi going from x naught to negative x naught, and then we come back down to we come down 2 pi units to come down to minus x naught. And this is our singularity here at pi I. Well, it's pi on the imaginary axis. The other thing we're going to do is use our function, and this again came from our earlier video, one of the first ones we did when we started complex analysis. The video was about functions of complex variables. We're going to use this formula here that cosh of z is equal to e to the z plus e to the minus z over 2. The next thing I need to do now is express my closed curve contour in terms of the 4 segments. This will be my first segment, my second segment is going up, the third segment going across, and the fourth segment coming down. So the first segment is here, going from minus x naught to x naught. And then I have my function e to the z over 2, 1 plus cosh z. My second segment is going up, and we're going from x naught to x naught. We're going up 2 pi units in the y direction, which is the I direction. So we're going from x naught to x naught plus I 2 pi. And here's my function. The next portion is going across. So we go from x naught to minus x naught, but we're up at 2 pi in the I direction. So we have x naught plus I 2 pi to minus x naught plus I 2 pi. And then finally, we're going down from our minus x naught plus 2 pi I down to x naught. So from minus x naught plus 2 pi I to minus x naught. The next step is to take the function I am integrating, e to the z over 2 over 1 plus cosh z, and for cosh z, I'm going to plug in my formula here to express cosh z in terms of the exponential form. So I'm going to factor out my e to the z over 2, that's in my numerator. Then I get 1 over 1 plus, and for cosh z, I write e to the z plus e to the minus z over 2. I make this one a 2 over 2 so I can do my addition. And then finally, I put this 2 on the numerator, so I have e to the z over 2, 2 divided by 2 plus e to the z plus e to the minus z. So that I have space to do each of these 4 integrals or explore the integral over each of the 4 segments, I'm going to kind of summarize everything and clear out some space here. The things I have summarized, I moved my segment, my closed curve here with the 4 segments. I have my formula here expressing my 4 different segments, segment 1 across the real axis, segment 2 going up, segment 3 across the top, and segment 4 coming back down. And then I also have my transformation of the function that I'm integrating, e to the z over 2 divided by 1 plus cosh z. Using this cosh z equals e to the z plus e to the minus z over 2, I have my final form e to the z over 2 times 2 over 2 plus e to the z plus e to the minus z. Now I'm ready to start my 4 integrals, or integrals over each piece. I'll do the first one, no, actually I'll do the second one first. Here I have my original integral from x naught to x naught plus I 2 pi. Now working on the function I'm integrating using this new form here, which has the exponential form of cosh z, I plug that in here. So now I have my integral of 2 e to the z over 2, so I just multiplied these 2, and then the denominator is 2 plus e to the z plus e to the minus z. Also, on this portion of our integral, the vertical portion, our x naught stays constant and our y varies. So z is equal to x naught, that's constant, plus y is still varying. That means our dz is equal to I dy. Since x naught's constant, it goes away. It's y that's changing. Now I can replace my dz with my I dy, which I did here, and I replace my z with x naught plus iy. Remember, x naught is constant, so I have e to the x naught over 2 plus iy over 2, and I'm just doing this portion here, replacing this z over 2 with this z over 2, divided by 2 plus e to the x naught plus iy plus e to the minus x naught plus iy. Over here I have my 2i, that's just this 2 times this I. For whatever reason, I felt the need to multiply them and put them all in the numerator. Here, I just do some algebra, so I have e to the x naught over 2, e to the iy over 2. And I do the same property of exponents, where instead of adding the exponents, I just multiply in the denominator. Looking at this term as x naught approaches infinity, because remember, we're really integrating along the real axis, so this minus x naught and this x naught need to go to infinity. Looking at our integrand and where our x naughts are, in the numerator, we only have e to the x naught divided by 2, whereas in the denominator, we have e to the x naught. So since this exponential power of x naught is greater in the denominator, it'll go to 0 faster, or this whole, than the numerator, which means the whole integral, the whole integrand goes to 0. Similarly, our integral on path 4, that's this one here where we have my minus x naught going to infinity. The integrand is the same, but the behavior here of the minus x naught, it's going to dominate similarly in the denominator, so this integral is going to go to 0 as well. I've indicated here that this second path and this fourth path, the up and the down, tend to 0. Next, I'm going to do the third path, that's along the top here. We'll see that it's equal to the bottom path, but the third path, the x naught, but it's raised at 2 pi I, and then it goes to minus x naught 2 pi I, and then our integrand. Again, I substitute this formula here, the exponential form of Cosh, into our integrand. And as I mentioned, the integrand itself is the same, and we'll see that this limits of integration for x naught plus I 2 pi is equal to the same limits of integration from x naught to minus x naught. That's on path number 1 here. I'm going to use this form here with the x naught to minus x naught just because it's a little shorter to write. Now looking at the integrand, I'm going to bring my 2e to the x over 2 down, and then looking at e to the I 2 pi divided by 2, so we have e to the I pi. So thinking of our unit circle, the radius is equal to 1 for e to the I 2 pi, and then if we go around pi radians, we're going to get to the value of -1. So this e to the I 2 pi over 2 is equal to -1. Similarly, this e to the I 2 pi, if we go around 2 pi radians, we come back to +1. So this leaves us with e to the x. Here, if we go in the negative direction, 2 pi, we still come back to +1. So that's where these ones come in, which simplifies to 2 over e to the x over 2, divided by 2 plus e to the x plus e to the minus x. Converting back to the Cosh formula, we have this exact expression. So now we have e to the z over 2 divided by 1 plus Cosh z. Now we have our closed interval, which is equal to the sum of the 4 paths. 2 of them go to 0. The other 2 are equal, so that's going to be 2, limit as x approaches infinity of the integral negative x naught to x naught e to the z over 2 divided by 1 plus Cosh z. You can also see why the path 3 and 1 are equal as x naught approaches infinity, that plus I 2 pi, that's going to be negligible. Then what this implies, if we divide both sides of the equation by 2, and also remember that this path integral, the whole point of our closure is that closed path integral is equal to our real integral over here. And all of that implies that our real integral, negative infinity to infinity, e to the x over 2 divided by 1 plus cos x is equal to 1/2 our closed integral of the complex function e to the z over 2 divided by 1 plus cos z. And now, because we have an integral over a closed contour, we can use our residue theorem. Since the contour encloses the singularity z equals I pi, we need to find the residue at z equals I pi. I promise this problem is actually wrapping up. To give myself more space, I summarized things here. I still have my Cauchy formula in terms of exponents. I have my closed curve integral in terms of my integral over 1 and 3, which gives me my real integral is 1/2 the closed curve integral, which contains, the closed curve contains our singularity z equals pi I, so we need to find the singularity, we need to find the residue at z equals pi I. You can expand this completely out using the Taylor series for e to the z over 2 and then the Taylor series for cosh of z, because both of these are analytic. You don't need a Laurent, but you'll need a Taylor series. You'll get negative exponents since the cosh z is in the denominator. But I wanted to use this residue formula. I feel like it makes things a little bit easier that we had from our last video where we took for a pole of order n. We'll see that this is order 2 down here. We need 1 over n minus 1 factorial limit as z approaches a, the n minus 1 derivative of wz times z minus a, that's our singularity raised to the n. This gets rid of the singularity, and we're left with the limit as z approaches a of the derivative of wz. But to use this, it's hard to see the singularity here in cosh z, so I am going to use the Taylor series expansion for cosh of z. So to expand cosh of z, we have the Taylor series, and this is given in the book, and so I was lazy and I didn't actually expand it myself. But cosh of x, because it's actually a Taylor series, it's analytic, is equal to minus 1 minus 1/2 z minus I pi squared minus 1 over 4 factorial z minus I pi to the 4th, and that's all we need. So I put that in my integrand, so I have e to the z over 2, and my 1, it cancels out with this negative 1, so I'm left with this part of the cosh series, minus 1/2 z to the minus I pi over 2 minus 1 for 4 factorial z minus I pi to the 4th. And I'm going to use this, again, residue formula for a pole of order n. Now I'm going to use my residue formula as well as the fact that the denominator here is dominated by the z minus I pi squared term. So I'm going to ignore the rest of the terms. So plugging into my formula, here I have a pole of order 2, so n is equal to 2. 1 over 2 minus 1 factorial is 1. Limit as z approaches my singularity at I pi. Since n is equal to 2, I only need the first derivative of e to the z over 2 minus 1/2 z minus I pi squared. And then in my formula, I multiply by z minus singularity to the nth, for the n pole, the n order, in order to get rid of my singularity. So that's z minus I pi squared, which cancels this term out over here, and I'm left with the limit as z approaches pi I, my minus 1/2, I just invert that to minus 2, derivative now of e to the z over 2. Taking the derivative, that gives me a 1/2, which cancels with the 2, so I'm left with the limit as z approaches I pi. The minus stays, the e to the z over 2, plugging in I pi over here divided by 2, so I pi divided by 2 on the unit circle, if you go over, and I'm going to use this circle here, if you go over pi radians, you end up at, oh no, you're only going over pi over 2 radians, sorry. So if you go over pi over 2 radians, you end up at I, and then you also have this negative sign here, so you're at negative I. And now we can say our integral, our real integral, the original integral from negative infinity to infinity, e to the x over 2 divided by 1 plus cos x is equal to, over here we need this 1/2, and then the residue theorem, 2 pi I times the residue minus I, which is equal to pi. And that is the end of this problem. So now that we've looked at this problem here, that we have closures with non-zero contributions, the next problem we're going to look at is solved with something called the principal part of an integral. And the problem that it addresses is if along our path of integration we have a singularity A. The principal part of an integral says when the integrand of a real valued integral has a singularity for some value of x over the range of integration, the value of the integral is undefined. So for example, if we look at the integral from negative infinity to infinity of 1 over x cubed dx, it's undefined because we have this singularity at x equals 0. However, in this example, since 1 over x to the third is an odd function of f, it's tempting to claim that the value of this integral is 0 because the negative infinity on the left of x equals 0 is canceled by the positive infinity on the right of x equals 0. To back this intuition up, we use something called the principal part of an integral, which takes the original integral and removes an infinitesimal region around the singularity. So we call this the principal part integral, so denoted PP for principal part. So our integral from negative infinity of 1 over x cubed is defined to be the limit as epsilon approaches 0 of negative infinity to negative epsilon of 1 over x cubed plus epsilon to infinity 1 over x cubed. We can picture this path here. We have our real number line, and then we have A, our singularity on our real number line. And then we have kind of a little epsilon, this little circle or half circle around A. So first, the distance from the end of our path, the black path to A, that's our epsilon, which is also over here, this yellow part, from the A to the positive A plus epsilon. So again, this point here where we stop integrating is A minus our little epsilon. This part over here where we start integrating again is A plus epsilon, and we're going to take epsilon infinitesimally small, so that's the limit here. Epsilon approaches 0, and again we're going from negative infinity up to negative epsilon. This actually assumes we're centered at 0, our singularity is at 0, which it is for x equals 3. So it's 0 minus epsilon, which is just minus epsilon plus, and then our 0 plus epsilon, which is just epsilon, to infinity. From here, we can just integrate. So the integral of 1 over x cubed is minus 1/2 x squared, and we evaluate that at negative infinity to minus epsilon, and then this integral here is the same, 1 over 1/2 x squared, evaluated at epsilon to infinity. When we plug in the infinities, those go to 0, so we're left with minus 1 over 2 epsilon squared plus 1 over 2 epsilon squared, which is equal to 0. And in general, not just for this example here, but the principal part of many real integrals can be evaluated by closure and then the residue theorem. And to show this, we're going to consider a general real function wx that blows up at x equals a. There's our singularity. The principal part of this integral is, we denote that pp, principal part, negative infinity to infinity dx of wx is defined as the limit as x approaches 0, and now we have our general form from negative infinity to a minus epsilon of wx plus, now we're at a plus epsilon to infinity wx. Here, we are still talking about real valued functions. We've done nothing to move to the complex plane so far, right? All we've done is we've kind of broken this up into two integrals, which we could do without having to move to the complex plane. But because we want to now use closure and the residue theorem, we're going to transform this integral into a complex integral. And I think it's kind of funny because when I say we transform this integral, it sounds like we're doing something fancy, but actually we're just changing the x to a z. Although, conceptually we're moving to the complex plane. And so again, we're going to transform to an integral in the complex plane. And now we can use closure so that we have this closed curve integral, which is equal to this principal part here. But now we also have this little circle that goes around the singularity. So we have the semicircle around the singularity. We denote the curve with this U because it kind of looks like this shape, the open pointing up semicircle. But we also have this semicircle that gives us the closed curve, this part over here, which we denote with the upside down U, as we did when we did closure in our last video. When we use the principal part and we do this closure and then use the residue theorem, we have this added part here, which is the semicircle around the singularity. So let's do an example to illustrate this. I brought over a few ideas from the previous page. The principal part from negative infinity to infinity is defined as the limit as epsilon approaches 0. We're going from negative infinity to a minus epsilon, and then this a plus epsilon to infinity. And then also our closed curve integral now is equal to the principal part plus this little curve around the singularity plus the semicircle that gives us the closed curve. The example we are going to do is evaluate the principal part of the integral 1 over x squared plus 1, x minus 1. And we're given that this is the limit as epsilon approaches 0 of negative infinity to 1 minus epsilon. We're concerned about this singularity, 1 over x squared plus 1, x minus 1 dx plus 1 plus epsilon to infinity, 1 over x squared plus 1, x minus 1 dx. And you might ask what happened to the singularities here because we can factor x squared plus 1 to x minus I, x plus I. Well, this here, remember, this is a real valued integral. X stands for a real variable, and we're doing integral of a real function. This is a real valued function, so we don't get to factor this to x plus I and x minus I. But that's kind of nice because we can ignore those singularities now. Now I use this formula here. The principal part is equal to the closed interval minus these two pieces. Here's our closed interval minus this U, that's the circle that goes around the singularity, minus this U, the semicircle that gives us the closed path. We're going to start with the integral of this circle here. And the integral is going to be equal to 0 since as z increases, this 1 over z cubed, essentially the denominator, is going to blow up. And so you're going to get 1 over z cubed approaches 0. And you could ask me, since all three of these parts have the same integrand, the same function, doesn't the 1 over z cubed still go to infinity? And I'll say no, 1. Here, because you're integrating over a closed curve, you really do need to look at the residues. And over here, where you're going around the singularity, at this point, your circle is getting smaller, and so it's not going to infinity. And the way this upper circle, your radius is approaching infinity, again, because you're trying to capture the real number line as you go from negative to infinity, this circle also goes to infinity. So this trick here works only for this part of the curve where you're trying to close a circle, a semicircle, using the real number line as the bottom of your semicircle. We go to the next part, our closed curve, and I've already kind of mentioned this. To get the integral around our closed curve of 1 over z squared plus 1, z minus 1, we're going to use the residue theorem. So we need to find the singularities inside of C. And now, remember, now we are in the complex plane. So here we do need to factor z squared plus 1 into z plus I and z minus I so that we have z equals plus and minus I as two singularities as well as z equals 1. And I just had that written out here. We have simple poles at z equals 1, and that's inside of C. We also have the simple pole z equals I, which is somewhere here, so it's also inside C. And then we have z equals minus I, another simple pole, but it's over here in the negative part, the lower part of the complex plane, so it is outside C. And now we are ready to calculate residues. So looking at the residue of z equals 1, using our formula, the limit as z approaches 1 over z squared plus 1, z minus 1, and then we multiply by z minus 1 to cancel out our singularity, and we get the limit as z approaches 1 of 1 over z squared plus 1, which is equal to 1/2. To get the residue at z equals I, again using the same formula for simple poles, limit as z approaches I of 1 over z minus I, z plus I times z minus 1 multiplied by z minus I, that gets rid of this pole. So we can take the limit as z approaches I. That will give us 2I times I minus 1, which you can simplify to 1 over minus 2 minus 2I. If you want to get the I out of the denominator, you can multiply the top and bottom by the complex conjugate and simplify to I minus 1 divided by 4. And now we have, for the closed curve integral of 1 over z squared plus 1, z minus 1, that will be 2 pi I times the residue at 1, which is 1/2, plus the residue at I, which is I minus 1 over 4. We have one more integral to do, which is this one, the one around the singularity. For our last part, I cleared out some space. I kept my formula for the principal part, the sum of the three integrals, the closure, the singularity, the curve around the singularity, the curve that gives us our closed curve. I had the result for this part of the curve, the semicircle, which was 0. And then I have our result for the closed curve, which is equal to 2 pi I times the residues inside C. And now my last integral is this part around the singularity, which is the integral around this curve, 1 over z squared plus 1, z minus 1. To evaluate this, I'm going to blow up this part of the graph that shows our curve around the singularity, and I have this graph here. So I have a graph as we're approaching 1. So this is our point 1, which is our singularity, and we have this semicircle around the singularity. We have 1 plus epsilon here. On this side, we have 1 minus epsilon. Here we have our point z, that because we're integrating around this curve. So for z here, this is the phasor. Remember, phasor is just a name for vector in the complex plane. So we can write z as in terms of our exponential form. So that'll be our radius, which is epsilon e to the I phi, where phi is the angle between the real axis and our phasor z. And then the other way we can express our phasor z is this is the phasor z minus, the phasor 1. So this is also z minus 1. So we have our phasor z minus 1 is equal to epsilon e to the I phi, which I've written over here for us to work with this expression. So this means z is equal to epsilon e to the I phi plus 1. Then that means dz, when I take the derivative, I get my epsilon, and then the derivative of e to the I phi is just I e to the I phi, and then I have my d phi, the 1, it's a constant, it goes to 0. And then remember, our phi, then, for this curve, phi goes from pi, right? Pi radians all the way over to 2 pi radians. I'm going to use this information to substitute for dz epsilon I e to the I phi. So now and d phi. So I have my d phi And then in my numerator, I have my epsilon I e to the I phi. This over here apparently is equal to z squared plus 1, z minus 1. I have that worked out, so let's look at that. I started by looking only at this piece here. So the limit as epsilon approaches 0 of 1 over z squared plus 1, that's the limit as epsilon approaches 0 of 1 over, and then substituting z squared, I have epsilon e to the I phi plus 1 squared plus 1. As epsilon goes to 0, this whole thing goes to 0, which makes this easy. So the limit as epsilon approaches 0 is equal to 1 squared plus 1, which is simply equal to 1/2. And that's where I get this 2 in the denominator, and then z minus 1 is over here. It's equal to epsilon e to the I phi, which means now my integral over this little semicircle around the singularity of 1 over z squared plus 1 times z minus 1 is equal to the limit as epsilon approaches 0 of, and now our phi again goes from pi to 2 pi d phi of epsilon I e to the I phi, that was in our numerator, times 1 over our denominator, 1 over 2 epsilon e to the I phi. These cancel out, like a lot of this stuff. This epsilon, this I, no, the I doesn't cancel out, but the e to the I phi cancels out. So we have the limit as epsilon approaches 0, pi to 2 pi. Our d phi is here. I said our I did not cancel out, and our 2 is over here. So our final answer is going to be I pi divided by 2. And finally, then, the answer for our principal part is equal to the integral over the entire curve minus, well, we had this integral over this semicircle, which was 0, minus this integral over the semicircle around the singularity. So the integral over the entire closed curve was here, was our pi over 2 I minus 1 minus, and then we have our integral over the singularity minus I pi over 2, which gives us our final answer of minus pi over 2. Hopefully it all makes sense. I feel like this is a lot to take in, especially if you're at the end of the semester and you still have another section of the book to do. But anyway, hopefully at least it makes sense. So far, we've extended our ideas of the closure video here by looking at 2 problems and then solving them. The first one was closure with non-zero contributions. The second one is if we have a singularity over some part of the axis that we're integrating, or range of integration. Our final topic is not a problem, it's just an extra problem, which is definite integrals with sines and cosines. And we are going to derive a general formula to deal with this. So here we're going to look at definite integrals with sines and cosines, and these are real valued functions now. And I left some notes on the principal part of an integral. I don't even think we're going to use it, but I'll leave it here in case we do, and then if we don't, I'll get rid of it. And the idea is sometimes we can convert a real integral with sines and cosines into a complex integral and then use a circular contour of unit radius, and then we can use the residue theorem. So z equals e to the I theta, where theta goes between 0 and 2 pi because we want the unit circle, the entire circle, and then dz will equal to I e to the I theta d theta, which means d theta is equal to dz over iz. Now I want to convert my sines and cosines into exponential form and then into complex numbers. So we did this previously in a video talking about functions of complex variables. We used a Taylor series to derive this formula. Sine of theta is equal to 1 over 2i times e to the I theta minus e to the minus I theta. So this is the formula we derived in a previous video. We're going to use it now. And also, since z is equal to e to the I theta, I can also write this in the form of 1 over 2i z minus 1 over z. For cosine, I have cosine theta is equal to 1/2 times e to the I theta plus e to the minus I theta is equal to 1/2 z plus 1 over z. Now I'm ready to substitute in my formula for I, which goes from 0 to 2 pi d theta w, some function of sine of theta cosine of theta. which is equal to my closed curve integral. Now for d theta, I'm going to substitute dz over iz, and then w for sine, I'm going to substitute z minus 1 over z 2I, and for cosine, I'm going to substitute z plus 1 over z over 2. So this is our formula here, and I'll give you an example to show you how it works. So I got rid of those notes about principal part, but I have our notes from the definite integrals with sine and cosine. This is what our original integral looks like. An integral from 0 to 2 pi d theta, some function of sine and cosine. I used our, z equals e to the I theta to calculate dz. I have our sine of theta, which I converted to this formula using z, 1 over 2I, z minus I over z. Our cosine formula converts to 1/2 z plus 1 over z, which means our original integral converts to d theta converts to dz over iz, and then w, our sine, converts to z minus 1 over z divided by 2I, and our cosine converts to z plus 1 over z 2I. The example we're going to use to illustrate that is to evaluate the integral I equals 0 to 2 pi d theta, 1 over 2 plus cosine theta. Here is my original integral. For d theta, I'm going to plug in dz over iz, and then I'm going to have my 1 over 2, and then for cosine, I'm going to plug in z plus 1 over z divided by 2. Again, that's just our formula that we derived in a previous video. The next thing I did, I missed my dz. Pretend like there's a dz in here. But the next thing I did is I multiplied the numerator and denominator by 2, just so I could get rid of this 2 here. So I factored out my 2 after I multiplied the numerator by 2. And then this becomes 4, and then I'm left with z plus 1 over z in the denominator. And then next, how did I get rid of this z? Oh, I multiplied in the z. So I have 2I, and then I have 4z plus z squared plus 1. I can pull out my 2I. That should have been 2 over I. I don't know if that makes sense. And then I'm left with dz over z squared plus 4z plus 1. So our poles, if we use the quadratic equation, is equal to z equals minus 2 plus square root of 3. That's inside of c. And then we have another pole, z equals minus 2 minus square root of 3. This is negative. Oh, it's not just negative. It's negative with magnitude greater than 1, which is outside our circle, our unit circle C, which means we need the residue at z equals minus 2 plus square root of 3. So we have the limit as z approaches minus 2 plus square root of 3 are 1 over z plus 2 minus square root of 3 z plus 2 plus square root of 3 times our z minus our singularity, which gets rid of our singularity, so we can plug in minus 2 plus square root of 3 into what's remaining, which is over here, and we get 1 over 2 square root of 3, which means our integral is 0 to 2 pi d theta 2 plus cosine theta is equal to 2 pi I times our minus 2I, which we get from over here, times 1 over 2 square root of 3, and that should give us, and this should be a divided by, sorry, that's why this isn't working out, but that'll give us then 2 pi over square root of 3. To review what we have covered in this video, we took up three separate topics to kind of complete our study of closures. And the first topic was closure with non-zero contributions. We were looking at when we integrate along an added segment, such as the semicircle, what happens if the closed contour does not equal to 0. And in our example, we kind of moved to a different closed contour, and then we had to make sure that our closed contour subtracted off any additions that our added contour added to our original integral along the real number line. The next thing we looked at was principal part of an integral. And this covered the problem as if there's a singularity for some value x over the portion that we're integrating over, the range of integration. So here, if we're integrating along the real line and there's a singularity at a, what we ended up doing is we defined what we called the principal part. And what the principal part is, it takes out an infinitesimally small circle around our singularity so that we just kind of avoid our singularity. So the principal part is defined as, over here, the limit as epsilon approaches 0. Remember, I'm saying it's an infinitesimally small circle around your singularity, are minus infinity up to a minus r epsilon. And then we add that to the integral from a plus a very small epsilon to infinity. And then from here, we take that integral into the complex plane so that we can add another curve and make this closed curve integral, and then use the residue theorem. And that's what this is here. Our closed curve then will equal to the principal part plus the singularity around the circle plus the semicircle that gave us our closure, so then we can use our residue theorem. Finally, we looked at definite integrals with sines and cosines, which really is not about solving problems of closures, but just a separate topic with sines and cosines. And the key was we used these two formulas here from a previous video very early on when we started talking about complex numbers for sine to convert that equal to the exponential form, which is 1 over 2I e to the I theta minus e to the minus I theta, and then e to the I theta is simply z, so then we convert it into complex number form of 1 over 2I times z minus 1 over z. We have a similar formula for cosine, so then our integral becomes 0 to 2 pi, substituting then our dz, or d theta, is equal to dz over iz over here, and then substituting for sine, our 1 over 2I z minus 1 over z, and then substituting for cosine here, we put in z plus 1 over z over 2, and we did an example of this. And that's it for this video. I know it isn't that long of a video, but it's a lot to take in because there are a lot of parts, especially over here. But the principal part is a very important part of real analysis. Anyway, that's it for this video. Thank you for watching.